All right, let's take a look at this. I'm aware that we are perhaps not all finished, but I would like to at least see where we were. Okay. So in order to talk about a probability distribution function, we of course need to discuss the random variable. In this case, what is the random variable that we have been given? Okay, so our random variable we are going to define as the number of heads. So if we are flipping 4 coins, what are our possible outcomes for what our random variable could be? What could we see here? Well, that's for an individual flip, we could see heads and tails. But for our value that our random variable could be, what could be a number of heads that we see? So we could see 4. What would the example be? What would the outcome be that gives us 4 heads? Heads, 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 heads. Okay, what else could we see? Heads, tails, tails, sure. Which would be what for our random variable value? 1. You said heads, tails, tails, tails. Sure. What else? What other values could our random variable be? Could be 2. Sure. What would an example be of one that gives us 2? Sure. Okay. 2 others. 3. Which would be what would an example be? Sure. Okay. And then last one, 0, which would be. Okay, so we have 5 different possible values for our random variable. I have given a sampling of what the outcomes could look like that give us this particular result. Now, if we wanted to do this precisely, which, ultimately we're being asked to construct a PDF, we need to know how likely each of these outcomes are, then we would need to essentially go through every single possible way to do heads and tails for a particular space and see of those what these values are. Which sucks as a process. That's not very fun. Certainly something that we could do, but would not be a very fun kind of prospect. For instance, if we're thinking about the number of locations that I have for where this T could go, I could have it first, second, third, or fourth. So there should be 4 ways to do this. If we're looking at heads, 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 well, there's only one way that we're going to be able to do that. Should be symmetric on the other side as well. This is going to be 4 ways. And this is going to be 1 way. And then I am going to cheat and say that I scrambled this all up. And there are, in fact, 6 different ways to perform our x equals 2 kind of thing that we have going on here. Okay. So total, how many different options do we have? We have 16 different options total. And so if we are constructing the PDF, value that we have 0, 1, 2, 3, and 4. What is the probability that we get 0 heads? How many outcomes out of how many total? 1 out of 16. Probability that we get 1. 4 out of 16. Probability that we get 2. 6 out of 16. 3 would be another 4 out of 16, and 4. It'd be 1 out of 16. Okay, so the brute force, not very elegant way to go about doing this would be exactly what I've kind of described here of literally listing out every single possible outcome. You could imagine that that gets very, very annoying very, very quickly. And it also becomes very, very hard to make sure that you didn't accidentally miss an outcome, especially if you don't have kind of the foreknowledge that I do of the fact that we should have 16 outcomes total. There is a more elegant way to go about doing this. It is something that we are going to explore in 5.3 with what is called the binomial distribution. But essentially, if we consider the number of ways that I can get two heads. So I've got heads, heads, tails, tails. And I want to know the number of arrangements, the number of heads, tails kind of combinations here that would give me two heads, two tails. Well, ultimately, how many results do I have total? How many coins are being flipped? 4. I know ahead of time, 2 of them are going to be heads, 2 of them are going to be tails. And so if I'm assigning, how many options do I have for what this first one could be? Well, assuming I don't know whether it's going to be heads or tails, I just have my 4 options. I know 2 of them will be heads, 2 of them will be tails, but how many options do I have here? 4 total, and then 3, and then 2, and then 1. So this would be like 4 factorial. Different ways to do this, except what happens if I get this heads first versus getting that heads first? What happens if I swap my heads? Does that change anything? No. What happens if I swap my tails? Does that change anything? So what do I have to divide my 4 factorial by? 2 factorial and 2 factorial, which equals 6. That is the 6 different ways that we can do that. So we'll look at that in greater detail tomorrow, but just a little bit of a precursor, how we could quickly construct this PDF rather than painstakingly constructing this PDF. But hopefully, once we see the outcomes, or at least the number of outcomes, the actual construction process makes a lot of sense. Any questions with, as soon as I have the number of ways, as well as that attached to a particular x value, how we generated the probability distribution from there? Particularly focusing on this bit here. Feel okay with where the table itself came from? Why the probabilities are what they are? Just number of outcomes over number of total possibilities, the likelihood that we see a particular type of outcome. All right. So we spent, I guess not Friday, but Thursday, taking a look at these new distributions, these probability distribution functions. Up until, or rather in Unit 3, when we were working with our distributions, we had a couple of different characteristics that we wanted to define in order to better discuss, better anticipate what is going on with our distribution. The main ones that we are going to continue to focus on today were the measures of center that we saw from 3.1, as well as the measures of spread that we saw from 3.3. So what is kind of our main go-to measure of center? We had 2 options, and then there's one that we're generally going to default to for the most part. What are our options for what measure of center could be? How do I find the center of a distribution? What's the middle of my data? Median or the average, the mean, okay? Of those two, we are going to be focusing on the mean. Generally speaking, we're going to focus on the average there. And then what was the measure of spread that is associated with the mean or with the average? So it's related to the z-score, very heavily related to the z-score. Very close. Z-score is the number of, yeah, it's going to be the standard deviation or the variance that we have that goes along with the z-score. Okay. So z-score, we're going to tie that in next week or maybe a little bit later this week. So we'll weave in z-score soon. But for now, we're just going to focus on establishing how do we find from a PDF the center and how do we find the distribution. Now, normally when we are using our just like data points, plugging things in, we don't really have to worry all that much about about means. In particular, because every single data point we often want to be as represented as every other data point. With our PDF, that is no longer true. Right, so if we're looking at a probability distribution function, there are going to be certain outcomes that are more likely than others that we want to factor in more heavily to our average. So for instance, looking at our first example here, we have an individual doing loads of laundry, as well as the likelihood for the week that they do a particular number of loads of laundry. We could go through and just take the average here, but this would not give us a very good picture as to what's going on because it's fairly unlikely that they're doing 0 or 1 loads of laundry. It's a lot more likely that they're going to be doing 2 or more. Right, this individual is more likely to do 3 than they are to do 1. They're more likely to do 4 than they are to do 0. And so treating 0 and 1 as having equal weight as the 3 and the 4 doesn't make a whole lot of sense. Okay, good news for us, though, is that we already have a tool that is tailor-made to dealing with this. The other good news for us is that the tricky part about using that tool is completely gone when we are looking at a PDF. And that is we can take a weighted average where the weights that we are going to attach to the particular values are just the probabilities or the kind of percentage overall that we want that particular value to contribute. So for instance, how much do we want this 0 to contribute to our total 100% of instances in which we're doing laundry? How much does that 0 count? How often does that 0 happen? What percent of the time? 0.09 or 9% of the time. And so if I want to know the average or the mean number of occurrences, well, we want this 0 to only account for 9% of our total instances. It's the weight and the value of x. Okay. Likewise, how much do we want this 1 to count for? I'm actually going to reverse this. Sorry. It's 9% of the time we see 0. It doesn't matter. I just want to be consistent with what we've seen so far. How much do we want the 1 to count for? What percentage? 16%, so 0.16. We want to be attached to that 1. How about the 2? 36%. Okay. And the 3, 27%. And the 4, 12%. And what we get by taking the sum of these weighted values is, it's up here, 2.17 for our weighted average. Now, 2.17 loads of laundry. Is that an actual like amount of laundry that would be possible for me to do in a week? Does 2.17 make sense as a, no, we'd expect to see like whole number values of laundry. So if 2.17 doesn't mean the actual value that we would expect to see for a week, how might we better understand what this 2.17 is trying to get across? If it's not going to tell us what's going on for 1 week, why would we talk, why is this 2.17 valuable for us? Yeah, so rather than referring to like a specific week, certainly if we were asked, hey, how many loads of laundry would we expect this individual to do? We might say 2.17, although again, that's a little bit nebulous because we wouldn't actually expect to see that value. But over a large number of weeks, we would expect the average amount of laundry to settle down at this 2.17. So we're not looking at a particular week, but if, for instance, I said what's going on over the course of maybe like 10 weeks, well, if each week we are doing about 2.17 loads of laundry, then we would maybe expect after 10 weeks to have done somewhere between 21 and 22 loads of laundry. And maybe over the course of 100 weeks, well, if every single week we're doing, again, about on average 2.17 loads of laundry, then we would maybe expect to see 271-ish loads of laundry done by then. So rather than giving us a kind of really, really good predictor for what's going on in a particular week, gives us more of a general estimate of what's happening over the course of like several weeks. Now, that being said, if we were asked to guess how much laundry would be done in a week, this 2.17 is probably our best guess. And even then it has meaning, right? Even then we're saying that it's probably going to be around 2, maybe a little bit more. Maybe we'd expect to see some of the time being 3, but generally speaking, we would expect to see about 2 loads of laundry done per week. That would be our expectation. Okay, so a couple of things to note here. First and foremost, the mean of our PDF is going to act a whole lot like a weighted average. And in this case, the weights are fairly straightforward. The weights are just the probabilities for that particular value of x. So for instance, if I'm looking at the mean for my PDF, we could think of this as the sum of my weights times my value of x, where in this case, the weights are very simple. The weights are just my random variable, the likelihood of my random variable being at that particular value of x. Again, don't get too bogged down by the notation. All we are saying is that this 0 happens about 9% of the time, and so that's the contribution that we want it to have. This 2 happens 36% of the time, and so that is the contribution that we want it to have. That's the weight that we are giving to it. That is the weight that we are attaching to it. And the way that we are generally going to be using this mean is as the expected value. It is our best guess as to what the value of our random variable should be if we just take a random selection. If we just do a random sample, the expected value of our random variable is just going to be that mean. Okay, so let's take a look at another example here. In this case, we are rolling a die and trying to figure out what is our expected value, or what is our average kind of value that we could see on the die that we roll. Right? Finding the mean number, in this case, of spots or values for what we have here. What do we notice as being a little bit different between, say, this distribution of probabilities versus what we saw from our first example? Okay, so it's given as fractions. That's certainly true. What else? Yeah, the probability for every single one is the same. Are we, if I roll a die, more likely to get a 1 than a 5? No, each one is equally likely. We would not expect one of these values to be weighted more heavily than another. And so if that's the case, then we probably would be able to just go ahead and take an average here and end up with the exact same value, because every single one is weighted the same, which is like our criteria for when to use an average instead of a weighted average. That being said, we can still, of course, approach this like a weighted average, and that is also going to get the job done for us. So for instance, what is this going to look like if I am looking for the expected value of x? What is my setup here going to be? How often am I going to see a 1? A sixth of the time? Okay. How often am I going to see a 2? A sixth of the time. Okay. How often am I going to see a 3? A sixth of the time. It's multiplying. Okay. How often am I going to see a 4? A sixth of the time. A 5. And then a 6. In this case, all equally likely. And you can plug this into your calculator. What you would get is that this expected value is exactly 3.5. Again, am I going to roll my die and get a 3.5? No, that's not what expected value is saying. Right? Expected value is not literally the thing that I am expecting to look at with my die. In fact, is there any particular value here that I would expect to see more frequently than the other? No, there's no reason to guess that it should be a 3 versus a 5 versus a 9 versus a, 9 we can probably eliminate, but versus a 2 versus a 4. All of them should be equally likely. So again, what does this 3.5 mean? It means that in the long run, as I roll a bunch of die, we would expect on average to see a value of a 3.5. Every time I roll a 1, I expect to roll a 6 as well. Every time I roll a 2, I expect to roll a 5. Every time I roll a 3, I expect to roll a 4. And so if I do a bunch of die rolls over and over again, then overall, on average, we would expect to see this 3.5. All right, questions here with our weighted average, or with our mean here. How are we feeling? The formula here? So the mean formula that we have here, this is just our weighted average formula, right? It's the sum of the weights times the values. And here we're saying that the weights are coming from the probabilities of our random variable being at that particular value.
And then
That just means we're adding them all together. So that's the, like, I don't just want to know my contribution from the 1. I also want to know from the 2 and the 3 and the 4, and then we add them all together to get that 3.5. Yeah. So all we're doing is essentially to find the mean for our PDF. It's a weighted average where the weights are the probabilities. Yeah. And that gives us a thing called the expected value. Yeah. Okay, let's take a moment. Take a stab at these first 2 examples here. And I will circulate, and we will see where we're at. Perfect. Thank you. That's great. So PEMDAS will take care of this kind of organically, just because multiplication is going to happen before addition, so it's going to multiply everything first and then add everything, which is the order in which we want things to go. If you're going to do parentheses, you just want to make sure that it's separating out the like that, which is essentially doing what the calculator does already, right? It's telling the calculator, hey, do the multiplication first and then do the addition, which is what it was already going to do. If it gave you 0, my guess would be you captured one of the, it communicated multiplication for the first term and the rest of it. Yeah. Looks good. Otherwise, it's working. I think you, yeah. Oh, yeah. Yep. You can just, yep. But like you can also look here and be like, okay, of these, how many of them have, like, what was this is the same as the finished. Awesome. Today is the 4th.
It's the third. Is it
It's the fourth.
It's the fourth.
I have to write a bunch of stupid mayonnaise.
You can't use that.
The reason I know the name was because it wasn't that hard. I had to like write.
Thank you.
There you go.
We get it.
Okay, let us take a look. All right, let's take a look at what we got here. What is my setup for this problem going to look like? So 0 times 0.06 plus 1 times 0.7, ... What did we end up getting? 1.23. Very good. Again, would we expect to see a family that took 1.23 vacations? No. But if we were to look at like 100 families, we would expect to see, on average, that 123 vacations have been taken. So again, even though we're calling it the expected value, that does not mean that this is the value that we literally would expect to see, but this is on average what this value is going to look like. Cool. For the second one, what did we get? Expected value was 1, which if we have 2 options and it's a 50-50 between each choice, then makes a lot of sense that you would on average see 1 girl between 2 children. Okay, I want to take a look also at this fourth example here. Mostly because the way we have to define the random variable is, I think, not necessarily the most obvious. And it gives us, this is like actually how we would use expected value to make decisions. So in this case, we are told that we are selling 1,000 tickets at $1 to draw for the chance of getting a television valued at $350. Question is, what is the expected value of monetary gain if we purchase a single ticket? Okay. So first of all, let's discuss outcomes here. What are my 2 possible outcomes? So win or lose? So either TV or no TV, or we could think of that as win or lose. So outcomes are either going to be we win or we lose. Okay. So we need a way to take this information, the outcomes that are whether we win or whether we lose, and we need to translate this into something to do with monetary gain. So what would make sense for our random variable to be defined as, if what ultimately we are looking at is monetary gain? It's going to feel redundant. Kind of gave it away. So it's going to process, hey, did we win or did we lose? And what do we want it to spit out? Okay, but that's the information we're getting in, and it's going to spit out the amount of money that we would expect to get based on that particular output. So this is going to be the amount of money gained from a particular outcome. Okay. So if we win, what is our monetary gain? $349. Liz, how'd you get 349? Yeah, and what was that guess based on? Have to pay $1 in order to enter. If you win, you get a $350 TV. Expected monetary gain, $349 if you win. How likely are we to win? What is the probability that our random variable is equal to 349? 1 out of how many tickets were sold? 1,000. Okay. And then what is our quote unquote monetary gain opposite if we lose? -1, because we lose $1. If we gain a -$1, we lose $1. And how likely is that to occur? Okay, so we have our values of x, we have our weights, we have all the information we need in order to compute the weighted average. Yeah. So let's take a look at let's take a look at what the expected value would be. So what is the expected value for each individual ticket? Well, this is going to be 349 times 1/1000, a 1 in 1,000 chance, plus -1 times 999 out of 1,000. Okay, plug this into our calculator and we get that the expected value should be -0.65. Okay, so what is the value that we're getting here? What is the x that's talking about here? What does this -0.65 represent? It's negative, so it can't be a probability. So what is this? Charlie, what were you saying? Yeah, it's like the expected amount of money that we'd gain, except it's negative, so it's actually the amount of money we lose per ticket, on average. Mm-hmm. So Merrick makes a really good point here. Is anyone that we look at, so 1,000 people buy the tickets, and we look at one person's winnings or losings. Is anyone that we're going to look at actually have a value of -0.65 for what they have earned? No. But this gives you insight into, if you were to buy a whole bunch of tickets, how much you would expect to lose on each ticket. So for instance, if we were to continue purchasing until we won, then it might tell us how much we would expect on average to lose per ticket that we are purchasing.
So you would eventually make a profit.
So you wouldn't necessarily eventually make a profit. You would eventually win, but you might not necessarily eventually make a profit. In fact, what this looks like, this -0.65, is 999 people losing $1 and one person gaining $349. So the vast majority of people are losing more, almost double the amount that we're expected to lose, and one person is making a lot more than what they are expected to be making. All right. But the way we would interpret this is we would expect each ticket purchased should lose that person 65 cents on average, right? Again, that idea on average. We're not actually saying that that person is going to lose 65 cents. They're either losing $1 or gaining that 349, but they're a lot more likely to lose that $1 than they are to gain that $349. Okay? If, on average, people are losing 65 cents per purchase, how many tickets are being purchased overall? 1,000. How could we figure out the amount of money that the people running the raffle are expected to make? So we could do 1,000 minus 350, right? They're making $1,000 and they are losing, quote unquote, the 350. So they should make 650. But where else could this 650 come from? Well, we're selling 1,000 tickets. And how much is the raffle team making per ticket? Yep. Exactly. Yep. Yep. Exactly. Yeah. This is one way to look at it where we are just saying, hey, we sold $1,000 worth of tickets. We're losing one TV. Here's the amount of money that we've made. But the other way is to say, hey, on average, we're making 65 cents per ticket that we sell. We're selling 1,000 tickets. Here's how much money we'd expect to make. Yeah. It's always going to be negative. If you look at any kind of raffle, I guess not any kind. I've seen one raffle where it was positive. And what you should do if the raffle is positive, gives you a positive expected value like this, is you should buy as many tickets as you can. Because you're very, very likely to break even your expected value being very high. But every time they're going to be negative. Because if the individual who's running the raffle is losing money per ticket sold, then that doesn't make sense why they would be selling the tickets up. Well, yeah, unless they're lying about the probabilities, right? Could be lying about the probabilities. All right, questions about our expected value here? How's this feel? How are we feeling? Feel good calling it expected value, even though it's not actually the value we expect, but it is the value we expect on average, being the operative word.
So every time, like expected value, you just multiply the x with the probability.
Yep. And then add all those weighted values together. Yep. Okay. So this is our mean. This is our average for our probability distribution functions. The other thing to talk about then is the spread for our PDFs. It used to be that standard deviation was nice and simple, right? We would just enter in all the data into L1, one variable stats, pull up the sigma or the S, and that was it. The problem is we can't enter the data in a way that tells us, hey, weight this more or weight this less or weight these in these particular ways. And so we're going to have to do a lot of these by hand. The goodish news is that once you get a little bit of practice, doing it by hand actually isn't too bad. It's going to look pretty ugly at first, but it's really quite straightforward. Okay, again, a lot of notation here. And we could run through kind of an algebraic showcase of why this is in fact the case. Reminder that we started with variance. And then what did we do to variance to get to standard deviation? Took the square root of variance in order to get to standard deviation. Just like that, we are again going to be starting with variance, and then we're just going to take the square root of our answer to get to standard deviation. If we recall, our variance was the average squared distance between the value that we are looking at, the data point, and the mu. But now we have another word for average. What is our other word for average? The mean, or new word, same as the mean. What's the new way we have to describe the average? Expected value. So now this is the expected value of our squared difference. Which, like, this is a totally fine way to conceptualize that, but you do a little algebra work, and what you end up with is what we see here. that standard deviation is the expected value from our squared x values minus the expected value of our distribution squared. What is the expected value of our distribution? We just said? Yes, and what does that give us? Which is the same as mu, the mean, exactly. So we are subtracting away the squared mean. And the way that we're going to find the expected value of the x's is pretty much exactly the same as the way that we're going to find the expected value, except instead of multiplying by the x's, we'll just multiply by the x squareds. Pretty straightforward. Okay, so let's take a look at our laundry example again. We had already calculated that our average, that our mean was 2.17. Now we are trying to figure out first the variance, and then once I have the variance, what am I going to do to it to get the standard deviation? Take the square root of it to get the standard deviation. Very good. Okay, so for this, we need to figure out our e of x squared, since we already know that e of x is equal to 2.17, right? That's just the mean. Okay. And what this is this, but I square the x's. That's it. So this is going to be equal to. Our probability is still the same. So 0.09 times 0. But now instead of times 0, it is going to be times 0 squared. Plus, we still have that weight of 16%. Now times 1, but instead of 1, it's going to be 1 squared. Okay. Plus. This is for that expected value of the x squareds. This is of the x squareds. So this is the first part of this formula that we're seeing here. So we're breaking this apart. We're going to approach it in two separate ways. This way has already basically been calculated. We just need to square the mu that we already have. And then what we're doing right now is we're just focusing on this part for now. Okay, so 36% times 2 squared plus 27% times 3 squared plus 12% times 4 squared. Which, again, in our calculator, it's literally just going back through. We're going to take exactly what we did before, and just on every single value of x, we're going to square. And we get that this is 5.95. Okay. Now, ultimately, what we want is not the expected value for our x squareds. Instead, what we want is the standard deviation. So we need to subtract our 5.95. This is our variance, rather, minus the mean that we calculated squared. So minus this mean squared, which gives us a variance of 1.2411. We have our variance. How do I go from variance to standard deviation? Take the square root.
Did 5.95 minus 2.17 squared?
Yep.
I didn't quite get that. Why did you do that?
Because that's the formula.
You go from variance to.
So we had our sum of the x squareds, or rather the weighted average with the x squareds, the expected value of the x squareds, minus the mean squared is the variance.
Okay.
Yeah. And taking the square root of both sides in order to get 1.114. Which we don't really have context for what this is, but we do have that intuition that the bigger this is, the more spread apart our data is, and the smaller it is, the more clustered together it is. Sure. And we'll look to quantifying that a little bit better throughout the course of this week. Should we take a look at another example? Yes? Resounding yes? Or we all feel ready? We're all ready for the quiz? Quiz on Thursday, which will not just cover this, it'll cover 5-3 as well, which we'll cover tomorrow. Yeah, just ready? Just send it, all easy. Okay. Well, we'll assume we'll look at one more example here, and then we'll run. Okay, we are being asked to find from the PDF that we are given the mean, because we haven't found that yet, the variance and the standard deviation for what we see here. Okay, so let's start with the mean. What's our other word for mean? Weighted average, which is the expected value. Yeah, just looking for the alternate definition, which we will find, as Abi has suggested, by taking the weighted average of exactly what we see here, using the probabilities as weights. So this is 5% contributing that 5, 20% contributing that 6. Not yet. This is just mean. Yeah, just mean. Times 7, 10% contributing to that 8, 15% to that 9, and then another 10% to that 10. Okay, so what is our expected value? Taking this, plugging it into our calculator, which I've already done right here. Nope, that's not the right one, right here. Gives us an expected value of 7.4. So the average here, 7.4 correct answers. Okay. Second piece to this is going to be figuring out the expected value of the x squareds. On its own, I'm sure this has meaning. I don't know what it is. To me, that value is meaningless. Right? It doesn't actually stand for anything. It is a consequence of algebraic simplification. Right? But we're still going to compute it, and it's still fairly straightforward to compute. We are going to do the exact same thing for the expected value, which we used to find the mean, except what am I going to do? Square all the x's. So it is literally the exact same thing that we saw here, except all of my x values are squared rather than not being squared. 56.6, whatever that means, which to us is meaningless. It doesn't actually hold meaning that we cared about. What are we doing with this? Well, it is a stepping stone to finding the variance. Variance is going to be equal to that e of x squared that we got minus e of x squared, our mu squared, which is equal to our 56.6 minus 7.4 squared, for which I get 1.84. Yeah, that one, the squared is already in it's already embedded in it. Yeah, exactly. Yeah, we've already done the squaring by squaring all the x's. Okay, so that's our variance. How do I go from variance to standard deviation? Take the square root, and so our standard deviation, the square root of 1.84, works itself out to be 1.356. Which again, we don't have context really for what that means within this particular distribution, but it's telling us something about how spread apart things are. Yeah.
The variance is like the x squared, which is
So this is its own thing. This is not variance. This is just in a vacuum. It's its own thing. It doesn't have any significance to my knowledge. I'm sure it does. I'm sure it does. I'm sure there are statisticians who are like rolling over in their grave when I'm saying that this is meaningless. But for our purposes, it's just like an algebraic like quirk that emerges from messing around with the expected value formula for the difference between the mean and the whatnot. And so it's just on its own, this value doesn't mean anything. It's only when we subtract away the squared mean that it means variance.
yeah, because I kind of got confused when we put like e x squared parentheses minus e x parentheses squared. So like, can I just put like mu parentheses?
Sure, this is the same thing as mu squared. Yeah, this is the same thing as mu squared. Yeah, absolutely. Right, good question. Other questions here?
Let's start working on our homework.
Sure. Yep. We got the rest of this time. Quiz on Thursday over 5.1 through 5.3. We'll cover 5.3 tomorrow. 5.3 is basically the extension on the bell work plus a little bit of this. Sure. Not too bad. And quiz on that on Thursday. And the 5.1, 5.2 classwork should both be open. So you guys have the rest of this time to work through that. If you have any questions, of course, feel free to ask. All that fun stuff.